So Cal 2 students, this is your textbook, and I'm in Chapter 6, Section 1. What I want to do with you is just kind of work through some of the concepts here in 6.1, explain exactly what's going on here with these integrals, and then show you a couple different problems. So the first thing I want to mention is that what we're doing in 6.1 first is trying to calculate the amount of displacement that an object receives, or the amount of displacement that some object incurs over a certain time interval. So the idea could be this: you might be moving. Let me grab my my board here. Bear with me. Okay, so let's say there's a road, okay, and you are standing here on the road, and then let's say you walk this direction for a while, and then for some reason you stop and you turn back around and you walk this direction. And let's say you do this in, like 3 seconds, and this in 2 seconds, so 5 seconds overall. Your total displacement is the movement from where you started to where you stop. So the displacement here, let's say when you first started walking, that this was, 10 feet. Okay, and then you came back another, let's say 6 feet. Well, your total displacement then, or the amount that you were displaced, is 4 feet. Okay, and how do we get that? Well, we took the 10 and subtracted off the 6. So the displacement, which is this, is 4 feet. So displacement is the overall, the end result. How much did you move from where you originally started? So displacement that's different than the distance that you traveled. The distance that I traveled that's equal to 16 feet, because I went 10 feet this way and then I went 6 feet back. So the distance traveled is different than the displacement, and that's just obviously the total movement that has been incurred. Okay, so we'll say it's the total movement that's been observed. So let me give you some examples, okay? And we're going to go through and we're going to do some integration techniques and calculate some things. So let's say, for example, that you were walking at 3 miles per hour. So let's say we were walking. I forgot my L in there, and that just became a big mess. So walk at 3 miles per hour. And let's say that we're always walking the same direction. Okay, so what I'm going to do, this is 3 miles per hour, so this is a velocity, because I've indicated that we're going 3 miles per hour in the same direction here. So if this is time and this is velocity as a function of time, and we're walking, let's say we walk 3 miles per hour and we do it for 4 hours. Okay, so 0 to 4 hours, and of course our function, I'll draw it here in green, our velocity stays constant at a height of 3. Now here's the connection that we want to make. If we add up the area underneath the curve between 0 and 4, this area will give me the displacement. So what I'm saying is this: if we integrate from 0 to 4 of this function. Now what is this function? Well, this function is v of t velocity is equal to 3. So we want to integrate the function v of t from 0 to 4, okay, with respect to t, with respect to our variable. All this says is we want to add up the area underneath the curve from 0 to 4 of a function that has a constant height of 3. Well, now watch what you get here. So what we want to do is we want to use the fundamental theorem of calculus. We want to find an antiderivative of 3, and of course we know that that is 3t plus some constant, but the constant doesn't matter here because it'll add and subtract, it'll cancel itself out. It'll add and subtract when we do the integration. So we want to evaluate 3t from 0 to 4. So that is 3 times 4 minus 3 times 0, which is 12. Well, what is this 12? This 12 is, of course, in miles, right? Because we're dealing now with position. Okay, we've dealt with position here. So what it says is that the area from 0 to 4 at a height of 3 is 12. Well, that makes sense, because think about it. I mean, if you just drew a rectangle here, and the base length was 4 and the height was 3, you would tell me that the area is 12. Okay, so of course, this was not hard to calculate. Well, what is 12? 12 is the displacement. So what this is saying is if you walked for 4 hours, okay, at a pace of 3 miles, at a constant velocity of 3 miles per hour, you would travel 12 miles. Okay, it's that easy. Well, what happens if you've got a function where the velocity is not constant like this? Okay, so let's go ahead and play around with a problem whose velocity is not constant. Let's say you are traveling with a velocity that's equal to, I don't know, let's say negative 2t plus 4, okay? From t is equal to, let's say, 0 to t is equal to 3. Well, let's take a look at this velocity function. So this, if I graph the velocity out, I would start out at a height of 4. I would have a slope of negative 2, which means I should hit over here at 2. So here's 1, here's 3, here's 4, so on and so forth. Let's go down with this a little bit. Here's negative 2, positive 2, whoops, and negative 4. Okay. Now, so we would have our velocity function would start at a height here of 4, and then of course it goes down 2 over 1, down 2 over 1, down 2 over 1. Close enough. It's not easy to draw a straight line with this tablet. Okay, so you just have to bear with me. Now the area underneath here describes our displacement. Okay, and also the distance traveled. Now, but watch. From 0 to 2, our velocity is positive. For example, at t equals 0, our velocity is 4. Well, let's do this in miles per hour. So it's 4 miles per hour. At t is equal to 1, our velocity is negative 2 times 1 plus 4, which is 2. So what I want you to notice is that we're slowing down. We're decelerating over that time period. From 1 to 2, excuse me, from 0 to 1 seconds, we still have a positive velocity, but we're slowing down. It's like if you threw a ball up in the air, okay, its velocity heading up would be positive, but it would be decreasing. It would be slowing down, right? So that's what's going on here. So what it means is between 0 and 1, okay, the object, let's say the object is right here to start. The object travels faster between 0 and 1, and now it's traveling a little bit slower, and then it'll travel slower, okay? And then it'll hit here at 2 seconds. And at 2 seconds, now the velocity is going to come back. It's going to force the object to come back this way. So the object went out with a positive velocity, and over that time period it's coming back. And that's what this negative piece right here is. Okay. Now, to figure out the total displacements, what we want to do is we want to add up this area and add up this area. Now here's the problem. This area down here, when I integrate, is going to come out to be negative. This area up here is going to be positive. So they're going to cancel one another out. And that's good because, and so it's not necessarily a problem, because we're going to have a positive movement and then a negative movement, right? And so we're going to end up going out and coming back a little bit. And that going out is going to be represented by this area, and the coming back will be represented by this area. So watch. If I integrate from 0 to 3 of the quantity negative 2t plus 4, that's a 4, with respect to t, this will give me the total displacements of the particle or the person or whatever it happens to be. Okay. Now clearly this is equal to 0. Hang on one second. Okay, just want to make sure we're still recording. From 0 to 3, oh, excuse me. From 0 to 2 of negative 2t plus 4 dt plus 2 to 3 of negative 2t plus 4 dt. What I've done is I've taken this area and this area to split them, okay? So, and I can do that, right? That's one of my rules is I can split up the interval of integration here. So this guy right here, let's get an antiderivative for this. So this will be negative 2t squared over 2 plus 4t, okay? Plus the constant, right, of integration. Okay, that's going to go away when we use the fundamental theorem. So these 2's cancel out, and so I get negative t squared plus 4t plus the constant. So this guy over here will be negative t squared plus 4t evaluated between 0 and 3. So that'll be 3 squared plus, let's just make sure I've got this all down right. Negative 3 squared plus 4 times 3 minus, so this guy, subtract off. We got to make sure we do the whole thing. So minus, it's not going to matter over here. That. So this will give me negative 9 plus 12 minus 0 minus 0. So this will give me 3. So what this tells me is that the object overall is 3 feet, okay, or 3 miles, or whatever units I'm working, 3 miles away from where it started. So its total displacement, the total amount of distance that it moved was 3 miles. Okay, when I say total amount of distance that it moved, what I mean is the overall, the end result is 3 miles. Now the amount of distance that I actually had to travel, well, that is going to be given kind of by these two things here. So watch how I can separate this. So this guy we know right here is, we already know the antiderivative. Okay, so we need to take negative t squared plus 4t and evaluate it between 0 and 2. And then take negative t squared plus 4t and evaluate it between 2 and 3. Let's see if I can fix that. Here's 2. There we go. Okay, so let's plug that in here. Okay, so that's going to be negative 4 plus 8 when I plug the 2 in. Okay, minus 0 plus, now this one's going to be a little bit harder. So we'll plug the 2 in here first. Excuse me, we'll plug the 3 in here first. So that'll be negative 3 squared, okay, plus 4 times 3 minus the 2 plugged into here. We'll do negative 2 squared plus 8, like that. Okay, so this would be negative 4 plus 8. Now I'm going to get a number out here instead of combining these right away. I understand that this cancels with this over here. I got that part. But this will give me 4. This over here gives me negative 9 plus 12 minus negative 4 plus 8, or minus 4. So this will be 3 minus, minus 4. Like that. Now here's what I want you to notice about these two pieces right here. This guy and these two guys. Okay. Between 0 and 2 seconds, this right here, this area between 0 and 2 seconds, we traveled 4 miles. Now, between 2 and 3 seconds, 3 minus 4 is negative 1. We traveled 1 mile. So our total distance traveled that's 5 miles. However, our displacement is given by this distance, which is 3 miles, which is that number down here. So the displacement is different than the total distance traveled. Now, what's the general formula that we need to use here? Well, if we want to find the displacements on a time interval from A to B, the displacement that's equal to the integral from A to B of the velocity function dt. If you want to find the total distance traveled, that's equal to the integral from A to B, but we have to take the absolute value of the function. The reason that we do that, what this does, okay, let me draw out a picture of what this does. When you take the absolute value of a function, if you've got a function, let's say that looks like this. Let's say this is f of x. When you take the absolute value of f of x, what that does is it takes all the y values and changes their sign, makes them positive. So what's going to happen, these guys will all stay the same, but these guys that went below will come back above. And so this yellow line is the absolute value. And what that does is, if you look at the area, it changes this from a negative to a positive. And so if you go back up, what that would do here is that would take this guy, make it go like this. And so we would be calculating this area. And if you take 4 plus 1 instead of 4 minus 1, 4 plus 1 is 5 miles. So, again, to recap, displacement, you want to integrate over your time or your velocity function. You want the total distance that an object travels, you want to integrate over that time period, but you want the absolute value of the function. So hopefully now if we go back and you look at your textbook, this conversation now should make complete sense. You should be able to read through all this, which I would recommend doing. Read through it and try these example problems. So here's a check. Okay, all you do is click on this guy. Okay, and it gives you some stuff to work on. If we go down here, we can work on an example. I believe that this example, the displacement velocity, okay, gives us some questions here to answer. And then of course, if you click, here's a solution on how to work it. I really think it's worth your time right now pausing, okay, before you go on to anything else. Work A, B, and C, and then check your solution and make sure everything makes sense, especially these graphs right here.